All right, class, today we're going to be talking about the short-run behavior of rational functions. Last video was on the long-run behavior of rational functions. And if you don't remember what a rational function is, it is basically the result of dividing two polynomial functions, where the denominator polynomial function cannot be equal to the zero function, although the output values of q can sometimes be zero. And in this case, I want to highlight in this term, we're looking at polynomial functions with different zeros. So p of x and q of x have different zero values. So anyway, what we talked about last video was that the long-run behavior can be used to determine what the horizontal asymptote is if it exists. And if you guys remember, very briefly, if this has a degree m and this has a degree n, then if m is greater than n, that means it has no horizontal asymptote. If m is equal to n, then it does have a horizontal asymptote that can be found at the ratio of the leading coefficients of the polynomial in the numerator and the polynomial in the denominator. And if m is less than n, then you have a horizontal asymptote at y equals 0. So that's just a review of what we did last class. Now we're going to talk about what's going on in the middle, the short-run behaviors. And in this case, to find the zeros of the polynomial, we can find them by determining the zeros of the numerator polynomial. So to find the zeros of the rational functions, they are the exact same as the zeros of the numerator polynomial, okay, as we can see here. And that makes sense because in the rational function, which is p of x over q of x, whatever value makes the numerator 0 would imply that that is a 0 of the rational function as well. Okay. All right. So that makes sense. So all I need to do to find the zeros of the rational function is to find the zeros of the polynomial function that's in the numerator. Okay. The third thing we talked about last video 2 was to find the vertical asymptotes. Well, remember, to find the vertical asymptotes, we find the zeros of the denominator polynomial. So if the denominator polynomial has zeros, that will give you a hint, oops, that's wrong, for the rational function vertical asymptotes. So that implies that's the vertical, sorry, it's out of focus. So the zeros of the denominator would lead you to the vertical asymptotes of the rational functions. Okay? So let's take a look at an example. So here we have, again, a rational function, and in this case, p of x is equal to 25. And q of x, the denominator polynomial, is equal to this denominator in factored form. We like the denominator in factored form because it helps us easily find the vertical asymptotes, okay? So based off this, the first thing we do is we find the horizontal asymptotes. And let's see, well, the degree of the numerator polynomial is 0 because it is x to the 0 power. And the degree of the denominator polynomial, x to the squared times x, is degree 3. So if you notice, that means that m is smaller than n, or the numerator degree is smaller than the denominator degree. So that means that you're going to have a horizontal asymptote at y equals 0. Okay? Second thing we're going to do is look at the zeros of the rational function. And if you notice, the zeros of the rational functions are the zeros of the numerator function. So when is this numerator ever 0? Well, the numerator is never 0. The numerator is always 25. So that tells me that this function has no zeros. So it will never cross the x-axis, okay? Which makes sense because you have a horizontal asymptote that is at the x-axis. And then let's take a look at, do we have any vertical asymptotes? Well, the vertical asymptotes are when the denominator polynomial is 0. So here, we have x plus 2 equals 0. This implies that we have a vertical asymptote at x equals negative 2. And over here, since another 0 of the denominator polynomial occurs when x minus 3 is equal to 0, that means we have another vertical asymptote at x equals 3. Okay? So why is that of any importance? Well, we're going to take all this information and do basically a general sketch of this function without using a graphing calculator. So here I know I have a horizontal asymptote here, and I know I have no zeros, and I know I have, based off this information, vertical asymptotes at negative 2 and 3. Okay, and I know it will never cross this axis. So how do I figure out what's going on over here, and how do I figure out what's going on over there? Well, let's take a value that is to the left of x equals negative 2. And so let's just say negative 10. So let's take a look and see what negative 10 is when I evaluate it. For r, I get still 25 divided by, well, negative 10 plus 2 times negative 10 minus 3 squared, which looks like 25 over negative 8 times 169. Okay, which means that it's a very small negative number. So here negative 10 is like some number right here. Well, because I have a vertical asymptote here and a horizontal asymptote here, then my end behavior is going to look something like this. I do the same thing for something in between negative 2 and 3. So I evaluate r at 0, because that's there, and I get, again, 25, and then I get 2 times 9. Okay, when I evaluated 0 plus 2 is 2, 0 minus 3 is negative 3, squared is 9. So that number is 25 over 18, which is a little bit over 1, but less than 2, so it's somewhere right here. And because I have an asymptote, I know I can't be down here, so I have to do something like this, but then it has to do something like this as well, because it can't go down, it has to go up. And then to try and find what goes on over here, I'd pick a value greater than 3, so let's try r of 10 as instead of negative 10, and I get 25 over 12 times 49, which is a small number, which means my little graph is going to go like this. And I have the graph without even plotting in the graphing calculator. Okay? All right, one more thing we need to talk about is the idea of what happens if you have a rational function that can cross a horizontal asymptote. And I'm just going to touch on this briefly, and they talked about it more in depth in this book. If you were to graph this in the graphing calculator, you would see, well, we know based off our information that here's this function, and it's going to have a horizontal asymptote at y equals 1, because this is a degree 2 and this is a degree 2. But if you look at this, for very large values of x, infinity plus infinity over infinity squared, sometimes it's going to be above 1. And that's only because, as you can see in this graph, even though it's not the graph, we have several sections that are a part of a rational function, which means that one section may adhere to the 0 and one doesn't. It doesn't happen frequently, but if you were to graph this graph in the graphing calculator, one part or one branch of the rational function will actually cross the horizontal asymptote of y equals 1. I know, deep, huh? But it doesn't happen often. We just have to be careful about that. Just because it's a horizontal asymptote doesn't always mean all parts of the graph won't cross, okay? And the last thing I want to talk about is zeros. So if we go over here, sometimes we talked about earlier that when P and Q have different zeros, then you have these situations. But what if they don't have different zeros? What if the numerator polynomial and the denominator polynomial have the exact same 0? Well, then that means instead of an asymptote, you're going to have a whole, okay? So let's take a look at this example. Here we have these two polynomials, one in the numerator, one in the denominator. When I factor the numerator, I have a factor in the numerator that looks just like one of the factors in the denominator, which means even though I can't evaluate the function at 1 because it will provide a 0 in the denominator, it won't be an asymptote because if I were to cancel these out, I can evaluate 1 at this function just for what's left here. So that means we have a whole. So the graph of this would look something like wherever 1 is, instead of a asymptote, it would be a whole. And this whole would be a value when r is 1, which as we can see in this case is 3. So this one right here is the 0.13.